off last time. We were working on this problem, our yardstick truss again, and we had part A and part B, and we had completed part A here. So part A, we are done with that. For part B, they're asking us to find AB, AG, and FG. So let's identify where that is on our truss. So AB, AG, and FG. So that's those three right there. Now, remember, method of sections, the advantage is that we can cut right into the middle of the truss, and we have three equations, and so we can handle three unknowns. So we're going to do a cut right here, and we can go to either side of that cut. We can go to the left of the cut, we can go to the right of the cut. Let's say we just decided to go to the left of the cut for this one. So we're going to go to the left for this. It would be an FBD to the left of a cut through, and that's through everything that we wanted, which was AB. It was also AG and FG. AB, AG, and FG. Now, remember, when we're drawing those FBDs, if we look at the overall frame or the overall truss there, we're cutting through those, but that's the only thing that we're cutting through. And then whatever other forces show up in that purple loop that we've created are the only other things that are going to show up in that FBD. So that FBD is going to include these members here, which we did not cut through, but then we did cut through this member here, and that was going to be AB. We also cut through this member here, which was going to be AG. And we cut through this member here, and that would be FG. And then we do have some applied forces there. Let me zoom out a little bit more. We have an AY that's going straight up right there. We have an AX, which we said was equal to 0. And then we have a 4.905 newtons that's going straight down. And our AY we found was equal to 3.93 newtons. So we drew, let me zoom in here. We drew everything, all of our unknowns were drawn in tension, and the only ones, the only forces that are exposed are the ones that we ended up cutting through. So AB, AG, and FG, we would need to go ahead and add our dimensions here, and then we can solve for these forces by looking at our, we have three equations, and to solve for the three unknowns. And remember, last time, to solve for our three unknowns, and last time we had actually used a couple of moment equations. So remember, we can use any combination of three equations. We don't get more than three equations, but any combination of three equations on here, and to allow us to solve for those three unknowns. So I wanted to just draw that FBD. I'm not going to finish solving that, but the most important thing is that we can draw those FBDs. Once we draw those FBDs and we've got all the correct forces on there, then we can go in and we can solve for those unknowns. What did we find last time? Actually, when we did our zero force members, we found FG to be equal to a zero force, right? John Pember, do you remember that?
No, I'd have to look back at that actually. Hold on.
Oh, okay. So we could look back at that. Actually, FG we identified when we went through that. We identified FG to be a zero force. ID'd as a zero force member before. Now, I didn't even consider that when I was drawing this FBD. I certainly could have. I could have put an FG equals 0 there. Now, what if, though, for this FBD right here, if I have point A right here, what if I sum moments about point A is equal to 0? Look at that. If I sum moments about point A on this FBD, I get rid of AB, I get rid of AG from my equation. I get rid of AY, I get rid of AX. None of those are going to cause a moment about point A. The 4.905, it also goes away as well. And so actually, I'm going to find that FG is equal to 0 still. So we talked about the search and destroy for zero force members, and that'll always identify all our zero force members. The other thing that we talked about is that no FBD will ever contradict another FBD. Well, now we've seen two different FBDs, the one that we used to identify FG as zero force, and another FBD, some of the moments about A, also told us that FG was equal to 0. And then these over here, we also identified as zero force there. These two were both identified as zero force as well. And it doesn't matter though, because I didn't cut through them. And so it doesn't matter if there's zero force or if there's a million newtons in those. If I don't cut through them, I don't expose the force that's in those members. Okay, so for today's quiz, let's see if we can apply what we've learned so far to this problem right here, where we're asked to find the force in member JD. And JD is that red one right in the middle there. We've got all the dimensions for this truss. It's this big truss here. And the red one, I've made it red just to highlight it and make it stick out so we can see it. And so our quiz today is cut one. So if we were looking at this and we said, okay, we want to solve for JD, are we going to use cut one? Are we going to use cut two? Or will either of those work? And I'll go ahead and I'll start the poll here in a second. Okay, there's our poll. So what do you all think? Could we do cut one? Could we do cut two? Or will either one of those work for us? And let's go ahead, just kind of maybe give me your gut feel here. Without thinking about this too much, just say, okay, yeah, which one of those is going to work? Cut one or cut two or either. Just looking at that quickly here. Okay, I'm going to go ahead. I've got 70% have voted. I'm going to end polling here. Got 81%. And it's A is the most popular choice, and then B and C are tied. So 47% for A and then 27% both for B and C. Actually, C is the correct answer. Either one of those will work. But cut one is a good one, and I think most people were picking that one because it goes through the one that we're trying to find, right? Okay, so now cut one, well, let's look at how either one of those is going to work. And this full problem is up on Canvas under the supplementary problems if you want to look at this later. So here's cut one. Now, when we do cut one, notice all of our unknowns are drawn in tension. We decided to go to the left of the cut. It doesn't always have to go to the left. We could have gone to the right of the cut. That totally would have worked. All of our unknowns are drawn in tension. But how many unknowns do we have? We have 4 unknowns in that cut, but it's nice because the one that we're looking for, that one is exposed by that. Okay, now how we could solve this though is actually going to be cut one plus an FBD up here at J, which we have drawn down here to the right. And so if we, from this cut one, if we sum moments about point D equals 0, we're going to find FJK. And then once we know FJK, then this FBD at J only has two unknowns, and we can use sum of forces in the X and Y, and we can solve for DJ. So that's one potential option, is to make that cut. And even though there's four unknowns, also this cut is at an angle. You know, the main thing when we're making cuts, notice every time we make these cuts, we're not cutting through a joint, right? We're cutting through members. Even at this angled one, we're cutting through, like this cut one, it's cutting through like the middle of those truss members. We never cut at a joint. We always cut through truss members. That's really our only rule that we have to follow when we're making those cuts. So that one works. Cut 2 plus the FBD at J would also work. Cut 2 is this one right here. Again, notice we're cutting through the middle of those truss members right there. We would do essentially the same process. Even though this cut does not expose D to J, which is what we are looking for, or JD, whatever we want to call it, we would still sum moments about D equal to 0. We would find Fij, and then once we find Fij, then the FBD at J again would have two unknowns, and we could solve for those two unknowns. Okay, so either one of those is going to work here. So up on Canvas, pick either will work. That's the correct answer. Any questions about that?